you have the transitional functions that you have a state as the input, and then you consume input symbol, and then you go to another state. So I feel that's similar.
It's very similar. It's very similar, but it's slightly different from it. And I'm not an expert in cellular automata, so I won't go into it right now. But after the lecture, I can tell you why I think it's different. You had a question? Yeah.
What is the expectation over pi or over the next state?
It's over pi, but how is it different from taking it over the next state or taking it over pi?
Because the pi is stochastic or determined.
Okay.
The pi is determined, and there's no...
Wait. So it's always 1. If pi is determined, do we always know what the next state is going to be? Why not?
If you know pi, you just know the action, but you don't know what's the next state.
Okay.
Right? Because the transition from state is...
You're right. It's being taken over next states. That's actually a very astute observation. Thank you very much for asking it. So this expectation is trying to incorporate the probabilities you assign to the reward that you may observe if you follow policy pi onwards. You know the policy, but you don't necessarily know what the reward is going to be. Why? Because you don't necessarily know what state you're going to transition into. Does it make sense? Cool. So, today we're going to talk about algorithms to solve this MDP problem. What does MDP stand for? Markov decision process. What's an optimal policy pi star? An optimal policy has the highest or the optimal value function V star of S. That's one way of defining it. It chooses the action in each state which will result in the highest return. Is there any other way to put it? Well, you can go through the Q function definition. Optimal Q value, Q star of S and A, is reward received from executing action A in state S and following the optimal policy pi star thereafter. Two very intuitive, simple definitions. V star of S, how does it relate to V pi of S? If you have a set of or an array of V of S's for different policies, how do you select the optimal in that array? You're right. You select the one, you select a policy for which the value of V is maximized. This is what's being denoted here. Bill, do you happen to have the laser pointer? Oh, thank you very much. So, is it not working? Oh, there it is. So you can see here, V star or V optimal is the one that generates is a one that generates a maximum value in between different V pi's. There are different policies available. Let's go through an example. Let's say that I want to train an RL agent to go from this state, standing here towards you, to the door. One policy could be if you are standing to the right of the door, or if you're facing that wall, turn left and go forward. What's the value function here? What's the return here, or the reward? The distance to my distance to the door. That's the reward. That's the instantaneous reward. One policy is turn left and go forward. Another policy can be, if you're facing the wall, if your state is facing that wall, go forward, turn left, and then go forward. Another policy can be, if you're facing that wall, turn right, take a step forward, take a step backward, turn left again, and go forward until you reach the door. Which of these policies do you think is optimal, given the reward function? The reward function is my distance to the door. One of them was, if I'm facing this wall, turn left and keep going until I reach the wall. Another was step forward, then turn left and keep going. Another was turn right and then go back. Which of these do you think is optimal? Which of these do you think is more rational for me to do? The first one. Why? Takes less time. In other words, the sum of distances over time is minimized or minimal compared to other two options. Why am I talking about distance? Because distance is our reward signal here, is our reward function here. So if we have different policies, which one is going to produce maximum V or optimal V? The one that produces best values or optimal values of V. This is like a tautology. Now, what about Q? What's Q star of SNA? Again, it's the one that follows the optimal policy, a policy that maximizes the value of Q. And how can we relate Q star to V star? Well, Q star of SNA, based on the definition that we provided a couple of slides ago, is the expected reward, instantaneous reward in the next state, plus gamma, the discount factor, multiplied by V star ST plus 1, given that you start from state S and you take action A. Any questions so far? Great. Now, let's talk about Bellman optimality equations. Did anyone have the chance to go through the Bellman equations chapter of the book, or does anyone have a notion of what Bellman equation is or does? Okay. This is important. Read the Bellman equations chapter of the book. I think it's chapter 2. It's not too long, and it's very simple to understand. Study it on your own. So, Bellman equation is the basis of an approach to solving decision-making problems called dynamic programming. How many of you have heard the term dynamic programming? One nod over here, one half hand over here, another half nod over there. Cool, I can work with that. So, dynamic programming is an approach based on recursive optimization. What do I mean by recursive? I say the best action I can take right now, the best action I can take at time t plus 1 depends on the best action that I can make at time t. And you keep solving this iteratively and recursively. So how can we turn this optimality problem, optimization problem, or decision problem into a dynamic programming problem? One way is as illustrated here. We can say we have a V star of S. What does V star mean? It means optimal value function. V star of S is max A Q pi star of SA, right? This is how we relate V of S to Q of S. And now we're talking about V star of S and Q pi star of SA. Does this make sense to everyone? If not, let me know and I'll explain it. Okay. Now, what's this equal to? Based on the definition of Q pi of SA, we know that Q pi of SA is actually expected reward if you follow the policy pi, expected return if you follow the policy pi star, given that you start from state S and you take action A at that state. What is this equal to? If you go to the previous slide, you'll see that it's actually equal to this. RT plus 1, the immediate reward that you receive after taking action A at state S, plus gamma multiplied by this total sum, which in itself is equal to V star of ST plus 1, the next state, which is curious, isn't it? We have V star of S is something that depends on V star of ST plus 1. V star of S, let's say V star of ST at the current state, depends on V star of ST plus 1 at the next state. This is how a dynamic programming or Bellman equation formulation emerges. For those of us who are CS majors, we already know this formulation from our algorithms class. We know that it can be very easily solved. For those of you who are not familiar with it, unfortunately, I don't have time to go through dynamic programming. It's an easy concept. You were supposed to study it before coming to the lecture, but go over it. Just for now, it's good to know that if we have this sort of formulation, we can easily solve it. We can tractably solve it. We can write an algorithm that solves this for us in a computationally tractable manner. What about Q star of SA? What if we want to solve for Q star instead of V star? Well, Q star of SA, as we said before, is the expected reward, expected return over time, which starts with immediate reward in the next state plus gamma max A prime. This is another action that you would take at the next state, which on its own is equal to the transition probability of going from state S to S prime given action A, plus the reward that you would receive, the return that you would receive from that, plus a gamma max A prime, Q star S prime, A prime. This is again relating Q star of SA to Q star of S prime, A prime at the next step, at the next time step. As long as we can relate the value at current state to the value at the next state, we have a dynamic programming formulation and we can solve for it. So, many of you are not familiar with dynamic programming, and I assume some of the confusion in your looks is because of that. Do we have any other questions so far? Do we all agree, or can we agree on this for now as an assumption, that if we have such a formulation, if we can relate the current value to what emerges at the next step, we can solve it? Can we agree on this? Cool. So, in general, value under optimal policy is the expected return for best action from that state. That's what you assume when you're solving MDPs based on Q star. We'll go through an algorithm for that in a couple of slides. So, this is really important. If the dynamics of the environment, and by dynamics, we discussed this last time, by dynamics, we mean the transition probability and the reward function are known, then we can solve equations for V star or Q star using dynamic programming. Given V star, what then is the optimal policy? Which action A do you pick in state S? You have the answer in front of you, but can anyone describe it in a 5-word sentence? if we have V star, how can we derive pi star from it? Or if we have Q star, how can we derive pi star from it? Let's start with Q star. We have Q star. We have an optimal Q function that tells us what the optimal value of taking action A at state S is. How can we derive the optimal policy from this Q star? Let's say we have three actions, A1, A2, A3. We want to see what the optimal policy at state S1 is. What's the output of the policy function? It's an action, right? The optimal policy function gives us the optimal action, the action that produces the highest Q value, right? Are you with me so far? So if we have three actions, all we have to do is to calculate QS A1, then QS A2, then QS A3, and see which of these values is the highest. And then that particular A action that maximizes the Q function is going to be the output of pi star of S. Does it make sense? So it's a one-step search. When you have the Q function or you have the value function, you perform a policy, you perform a search to see which of these actions produces the best Q value or the best value given a state. And that's going to be create a table for you, which is your policy function. At state S1, taking action A1 produces the best value. At state S2, taking action A1 again produces the best value. This table is going to be your policy, your optimal policy. Any questions so far? So what have you learned? We've learned that if we can create a recursive formulation for either Q star or V star, we are able to solve it using some magic called dynamic programming. When you've solved it for Q star or V star, then we can simply find what the optimal policy is by doing a one-step search. Are we all okay with this so far? Good. That's a very good observation. Tell me more about it. Why would there be a memory problem?
Well, because you need to compute the expectation because the requirements function in yield to the so you have to see all this information.
That's very true. Yes. So
in the regular iterative methods, you just do one step, you use like the next one, you get well
in one slide. In the next slide, I will talk about the exact same problem. And you're right. There are memory problems. There are computational complexity problems, and we'll get to it. I'm going to record or deliver a lecture on deep reinforcement learning. In those cases, what's used is a memory buffer or a replay buffer. We'll talk about all that in a few seconds, but that was a very good observation. Thank you, Vic. So, what happens if there is more than one action that produces the optimal value? Let's say we are in state S, and in that particular state, both actions A1 and A2 produce the highest Q value. What do we do then? Both actions are the best actions that you can take. So you can take any. All of those actions are okay. We can just do a coin flip and randomly choose between the two or choose the one that's easier to perform. And talked about this here. Now, the assumptions for solving Bellman optimality equations, or the assumption in using dynamic programming to solve a reinforcement learning problem. First of all, we assume that we know the dynamics of the environment. Once again, what are the dynamics of the environment? What defines the dynamics of the environment? it's a tuple of transition probabilities, the probability of going from state S to state S prime if you take action A at state S, and the reward that you would receive if you go from state S to state S prime by taking action A. This is a very, very important assumption. It assumes that you know the dynamics of the environment. Do we always know the dynamics of the environment? Doesn't RL agent always know the dynamics of the environment? Let's think of the case of an RL agent whose aim or goal is to learn to play the game of Pong. When it starts, it doesn't necessarily know the rules of the game, it doesn't know the physics of the game, it doesn't know the reward function, and it has to explore the environment to learn about all of these, right? So, if we know the dynamics of the environment, are we really solving a reinforcement learning problem? Remember the first lecture. There are two kinds of sequential decision-making problems. One is planning, the other is reinforcement learning. Does anyone remember the difference between planning and reinforcement learning? So in planning, you have access to all of this information. In reinforcement learning, you don't have access to this information. If you have access to this information and you solve for it, you're solving a planning problem. If you don't have access to this information, you have to come up with an estimate of these parameters to be able to solve it using dynamic programming. That's where reinforcement learning comes in. Second, as your colleague said, sufficient computational resources is required. You need to have enough time and memory. One very important thing to notice when you read about dynamic programming and Bellman equation, there's a proof that says dynamic programming always converges to optimality, but at infinite time. So if you have infinite time, you're guaranteed to converge to optimality. Do we have infinite time? Some people are thinking about it. Do we have infinite time when we are running a dynamic programming algorithm? We don't. So there are cases where reaching optimality is not possible using dynamic programming. In those cases, we go with a best effort approach. And there's not always enough memory available. Like, let's assume the game of backgammon. I assume that we are all familiar with backgammon. Let's assume that the first assumption is satisfied because we can somehow code the transition probabilities, the rules of the game, and the reward function into the agent. But then there are 10 to 20 states in backgammon, which means that there are 10 to 20 equations in 10 to 20 unknowns, and we are solving nonlinear equations. These figures are, by the way, maximum number of states that are possible. So this is a very huge state space. Can we really fit it in a good memory? Can we do computation in a short amount of time? Not really. In such cases, which will be covered in more detail in our next lecture, we can use a neural network to approximate the value functions, policies, and models. We don't need to have an exact understanding of everything. We need to have an exact representation of everything that happens. Just an approximation in most cases or in practical cases helps. And that's how we come up with a compact representation. Can you think of another way of reducing the dimension of this problem?
Abstraction.
What do you mean?
So you have states that are very fine. They're units of one step. You could combine steps and abstract state or other parts of the task definition to a higher level than you have less research space.
That's very true. So if you can come up with a representation that can bundle states together or come up with some lower dimensional abstraction, we can solve it. There's a keyword that I've used it at least twice, and it's in your lectures. You've studied this. I want to see if you can think of this right now as a solution to this problem. The problem is our state space is huge. There are so many dimensions involved in it. What's the technical approach to reducing dimensionality? Guys, it's in your lectures. How about dimensionality reduction? Does it ring a bell? Okay, so yeah, go through your lecture slides on dimensionality reduction. That's one of the things that can be done. It's exactly what Bill explained, essentially abstraction, but a little more complicated than that. For now, let's assume that if you come up with an approximation using neural nets or some other means, you can save some space.
Right.
Yep.
Maybe if you give an example of a dimensionality reduction problem in the grid world, so what approach?
I'm going to add this in my deep reinforcement learning lecture because we are going to cover dimensionality reduction and ways of getting from pixels to representations of a game. We actually have that in the syllabus. So what about optimal policy? Do we really want a policy that always gives us the best answer for every state that comes up? Not in most practical situations. In most practical situations, all we need is for the policy to be optimal in situations we encounter. So if there is a situation that we encounter very rarely, we don't really care about optimality in those situations. We are bounded in time and computational power. So we are doing a best effort optimization. If we say, hey, let's say our optimal policy for me as an RL agent to get to that door, considering that I'm facing that wall, is to turn left and go forward. There's a very, very, very rare state, which is me facing upwards, lying down on the ground. We don't necessarily have to have an optimal solution for that state. We can just come up with any solution in that state because it's rare and we are going for a best effort solution. Any questions so far? Are we clear on the first two assumptions of solving this decision-making problem, sequential decision-making with Bellman equations and dynamic programming? Once again, the first assumption is know the dynamics of the environment. We know the dynamics. If we don't, we have to come up with approximations of it. And two, we have sufficient computational resources in terms of time and memory. We've seen this slide before. What are the components of an RL problem? We know that there's an agent, there's an RL agent. The RL agent has to perform a task. What's the task for the RL agent? For the example we've been using so far, the task is to get to that door from whatever state starts from. What's the environment? The environment in that example is this classroom. And that environment includes the dynamics of the environment, which is P and R. We'll go through that too. We know what a policy is, probability of doing action A in S. This is a stochastic policy. What's a deterministic way of denoting a policy? So a stochastic policy is a distribution. It's like this. What's a deterministic policy? How do we represent a deterministic policy? Is it a function or a distribution if it's deterministic? It's a function. So it would be pi of S equals A. We know the state value function. We know the action value function. We know about model. Model in general is both P and R. The transition probability P is the probability of going from state S to S prime if we do A. The reward function R S S A prime from doing A in S and reaching S prime. We already know what it is. Return is the discounted sum of future rewards. Total future discounted reward is also another notation. We denoted it by rho, if you recall from the previous lecture. And then we need to have a strategy to learn. We'll talk about that for the rest of this lecture. We may have some sort of value function, either state value or state action value. And what we need to keep in mind is we are always constrained by some bounds. We may be short in time, we may be short in computation power, or there are other constraints that we have to put into our optimization problem or solving the RL problem. Sometimes, subject to conditions, we have to learn the best policy that we can achieve given our constraints, like within a certain time frame. All right, so what are the algorithms that can be used to solve RL based on this dynamic programming formulation? One of them is policy evaluation. Another is iterative policy evaluation. We'll go through both in this lecture. There's policy improvement, and then there's policy iteration again. There's a difference between those, a subtle difference which we'll cover. There's value iteration. Asynchronous dynamic programming is not covered in our lectures. You can look into it from the book, but it's not part of our syllabus. And then we have generalized policy iteration. So dynamic programming is a magical thing we talked about that solves a recursive formulation in optimization. We said that we need perfect model PSS prime A and RSS prime A. And we want to compute either V star or Q star. Why either? Why not both? Exactly. Because if you have V star, then you can get Q star from it. You can derive Q star from V star, or vice versa. So let's talk about policy evaluation. Suppose we have some policy pi, which tells us what action A to choose in state S. Find the value function V pi of S of this policy, which essentially means evaluate that policy. We know the Bellman equation for V pi of S. We derived it in a few slides ago. And we know that we can solve it using this magical spell called dynamic programming. The problem is, it's a very huge problem computationally. We have S equations. What's S? Number of states, correct. S equations in S unknowns. So we need to iterate. This is a very computationally expensive way of going about solving this. So why do we call it iterative policy evaluation? Because we solve it through iteration through different states. We apply a sweep or a backup operation to each state to compute the value at that state. Each sweep, represented by this right pointing arrow, updates our current estimate of the value function. And then we update the value at state S using this equation here. The value at state S in iteration k plus 1 is the sum of the policy, this is assuming a stochastic policy, SA, the probability of taking action A at state S multiplied by the transition probability of going from state S to S prime given action A over all possible next states times the reward that you would receive plus gamma VK S prime. As you can see, we have the recursion we were looking for. Vk plus 1s depends on Vk s prime. What's k? Exactly. It's an iteration counter. Imagine a for loop or a loop in any kind. This k is the index of iteration. You're saying that at iteration k plus 1, v of s is calculated based on this equation here. In other words, we are using the Bellman equation as an iterative update equation. It updates the v's for all states iteratively. This is called a full policy evaluation backup. After many sweeps, will converge to v pi of s. Now, what do we do with this v pi of s? What's the point of having this v pi of s? Oh, what is the problem? So how can we get from v pi of s to pi star of s? What was that? Yes, so we have to iterate over different policies as well, right? We assume that we have a policy pi in the beginning, right? This is how we got to this v pi of s. We are evaluating a policy pi of s. So we have to explore over the space of different policies to be able to find v star, right? It's not just this hugely expensive or extravagantly expensive evaluation. We have to do something else over the state of different policies. So, start with arbitrary v values. Let's go through this algorithm here. Let's start with some v values, some random v values. Iterate and update until you get v for a certain policy, and then v pi is a fixed point. It solves the Bellman equation. So again, given a certain policy, we now have an evaluation of that policy, how good that policy is. Is it possible to improve policy pi? Yes, we can do policy improvement. This is what we discussed so far. Now, we have v pi for our policy pi. Can we choose a better action than that stipulated by pi? In other words, an a which is not equal to pi of s? The value of choosing action A in state S is the Q value, right? This is the definition of Q function or Q value. Q pi of S and A, this is the definition, is the immediate reward in the next state plus gamma V pi ST plus 1, which is equal to this. We've already derived this in our previous slides. If Q pi of S and A is greater than our current estimate, then we should choose A. Is it obvious why? Because A is giving us a better Q value than what the previous policy was giving us. Okay? Do this for each state. So you iterate over states, and you iterate over all possible actions in each state to see whether you can do better than v pi of s, and thus you improve your policy, because we are changing a policy that gets to something that gets us more return. One more slide and we're done for today. Improve the policy at each state. We get a new policy pi prime that's greedy with respect to v pi. Pi prime of s is arc max over a. It means find the action that maximizes this value here, and this is the equivalence. We've already derived this equivalence in previous slides. In this case, the new policy is better than the old one, and then we keep going from there. V pi prime of s is max over all possible actions. We want to find what action maximizes this. And then this is the Bellman optimality equation, and the value function and policies are optimal. If we keep going for a very long time, if we iterate over all spaces, and at each iteration, we iterate over all possible actions. Do you see the problem with this approach? We are able to greedily improve our policy, but there's a problem in this approach. How many iterations are involved here? One for evaluation of the arbitrary policy that we started with. One for iteration over states. Actually, no. One for evaluation, one for iteration over states, one for iteration over actions in each state. And these are nested loops. This is a very expensive operation computationally. That's why alternate solutions have been proposed. In general, this approach is called policy iteration because you're solving for optimal policy. As we said in the first lecture, it's not necessary to do policy optimization. If you can do value iteration and value optimization, you can still get to an optimal policy. You can derive optimal policy indirectly by optimizing the value function or the Q function. All right, we are out of time. Thank you very much for bearing with me. The slides are out there. Again, I'll discuss with Bill to see whether I can present the next lecture or I'll record it and give it to you. The next lecture is going to be on deep Q learning, which is the basis or one of the first algorithms proposed for deep reinforcement learning. There's a lot of hype going on around this deep RL bit. You can watch it and go through it, and you can learn about practical implementations of deep Q learning. There's going to be an assignment on implementing a deep Q network to solve a game, probably the old Nokia game Snake. I haven't chosen the game yet. I gave you a lot of information assuming that you know what dynamic programming is. And my assumption was proved to be wrong. Please study dynamic programming, go through the slides again. The video is going to be available. Go through the video. If you have any questions, it's vital that you come and ask me. This is a very interesting and very important topic. Do come and ask me if there is anything that you are doubtful about, after consulting Google, of course. All right, thank you very much.